In this video, we'll go ahead and we'll perform a calculation of delta G and see if the reaction would be spontaneous under conditions of constant temperature and pressure. So what's the reaction we're going to look at? Let's look at carbon tetrachloride that breaks down and forms carbon in the form of graphite and chlorine diatomic gas. And we'll go ahead and we'll just give you the values for delta H here. So delta H for this reaction is positive 95.7 kilojoules. And delta S for this reaction is positive 142.2 joules per Kelvin. We'll talk about how to calculate that in a later video, but maybe we can discuss a little bit why these things are the way they are. So first off, delta H is positive, which means that you are putting in energy. We can see that we're actually breaking 4 bonds between carbon and chlorine, and we're making 2 bonds between chlorine and chlorine. So probably, since we're breaking twice as many bonds as we're making, we probably have to put in some energy here. We can also see that we're taking 1 mole of gas and we're turning into 2 moles of gas. And so since gases are very chaotic, they have a lot more entropy. So it's no surprise the entropy is actually increased. Let's go ahead and calculate delta G at 25 degrees C. So we can calculate delta G at 25. Why are we doing delta G? It tells us whether a reaction goes. So if it's negative, it will go. If it's positive, it won't go. If it's negative, that means the entropy change for the universe goes up. So the equation is delta G is equal to delta H minus T delta S. So sorry, got an extra nubbins there. All right, minus T delta S. And the units have to be equivalent for us to do an addition or subtraction. So notice we got kilojoules and here we got joules. So we'll have to convert into a same unit for energy. And let's go ahead and use joules. So it would be 95,700 joules minus, we said 25 degrees C, so that's 298 Kelvin. And delta S then is 142.2 joules per Kelvin. So we can see the Kelvin would cancel out, so we'll have joules and joules, which is okay to add. And if we bring these all together, we get something like 53,300 joules. So actually, maybe converting to kilojoules would have been smarter here, so that would be positive 53.3 kilojoules. So what does that mean? Well, because it's positive, it means it will not go. So that is a non-spontaneous reaction. So delta G's got to be negative. It's got to fall down the Gibbs energy hill to go. And that is not going to happen without the input of energy. Now, interestingly enough, this is one where delta H and delta S are both positive. So they're sort of going in opposite ways. So delta H being positive makes this unfavorable from the point of being spontaneous. Delta S positive actually makes it favorable. So if we ramp up the temperature, maybe we can make this more negative than this is positive, in which case we can get the reaction to go. So let's go ahead and try and figure out the temperature where it would be spontaneous. So the trick to doing that is recognizing that delta G is delta H minus T delta S. And if we look at how this changes with temperature, we saw that at low temperature, delta G is positive, and as we increase the temperature, delta G gets more and more negative. Therefore, there must be a crossover temperature where it goes from being non-spontaneous to spontaneous. So if we can only find that temperature there, where it will be at equilibrium, right past there, it will be spontaneous. So how would we do that? Well, delta G is 0 at that point. So we can go ahead and we can say that point there is where delta G is 0. So we can say that that's the point where delta H and T delta S are exactly equal to each other. In fact, if we want the temperature, we can just divide both sides by delta S, and that gives us the temperature is delta H over delta S. So in our reaction here, delta H was, what was it, 95,700 kilojoules, so 95,700 joules. Sorry, what did I say? 95.7 kilojoules. And delta S was 142.2 joules per Kelvin. And if we do that division, we get 673. Now, in terms of the units are Kelvin. Make sure you know why. So just as a little aside, right, if we got joules divided by joules per Kelvin, remember when we divide by a fraction, that's like multiplying by the inverse of the fraction. So there we can see that Kelvin ends up being the units, and we would expect that for a temperature. And by the way, if we subtract 273, we get that in Celsius, so that is 400 degrees Celsius. So at 400 degrees Celsius, this would start to cross over, and at 401, 402, 403, right, 500, 600, it would be more and more spontaneous. So that's pretty awesome that we can actually use thermodynamics to say, hey, if a reaction doesn't go, is there a temperature where it will spontaneously go? So we can do that indeed. Wasn't that exciting?